as he started all the right before.
So welcome everyone. I would like to say a few words to introduce today's speaker, Dr. Lantao from Cornell University. So Lantao received his bachelor's and master's degrees in atmospheric sciences from Peking University. During his master's thesis, he analyzed data on the atmosphere of the Arctic and the Antarctic regions, which was collected by the Bureau of Oceanography in China. And in this way, his thesis was really about the variability of the polar vortices. And subsequently, he applied for graduate school here in the US at the University of Illinois in Urbana, where Professor Walter Robinson has worked for a long time on stratospheric variability and especially variations in the polar vortices. And so Lantao did his PhD there in 2010, and his thesis was about the impact of stratospheric changes on tropospheric circulation. And after his PhD, he became a research associate at Cornell University, where he worked with Dr. Gang Chen, and he has written several very interesting papers on the coupling between the stratosphere and troposphere, and also wave mean flow interactions and other aspects of the circulation of the atmosphere. So let us welcome Lantao.
Okay, second. Okay. Hello everyone. Firstly, it's my honor today to be here to present some of my works on the predictability of stratospheric warming events. Before I start this talk, I will first mention my co-authors, Dr. Walter Robinson in North Carolina State University, and Dr. Gang Chen in my department. This talk mainly comprises 5 sections. The first 2 sections is more like the introduction, which we will present the motivation and the scientific question we are planning to answer. And the next 3 sections is basically to the method we use to evaluate the predictability and the results for the stratospheric final warming events and sudden warming events, followed by a short conclusion. And firstly, just to give some background information for those people who are not that familiar with the circulation in the stratosphere. The left figure I show here is climatology, December, January, February, zonal mean, zonal wind. And the right panel is the June, July, August averaged zonal mean, zonal wind climatology. So here, what I'm trying to say is in the winter of the northern hemisphere and the winter of the southern hemisphere, there is westerly wind which is positive in the actual tropics of the stratosphere. This westerly wind is normally called the polar vortex. And we can see some kind of difference that northern hemisphere, the polar vortex is kind of weaker than the southern hemisphere. And in the summertime, this is the southern hemisphere summer, and this is the northern hemisphere summer. In the summertime, the stratospheric wind will become easterly, so that the polar vortex will break down. And in this figure, I'm trying to just give an example about the intraseasonal variability within the winter and the seasonal transition in the springtime. This is 1987, northern hemisphere, around 60 degrees north, zonal wind change from January 1st to end of June. And in the high latitude stratosphere, we can see from the previous slide that it's normally the polar vortex, which is the westerly wind, but sometimes it could transit to easterly. This transition from westerly to easterly means the breakup of the polar vortex in the winter time, which is also accompanied by a huge temperature increase in the polar region. And this, we normally call it the stratospheric sudden warming events. And on the other hand, because of the seasonal change of the solar radiation, the polar vortex will finally break down from the from winter to summer, so that in the springtime we can see this transition from westerly to easterly again. This warming events, we call it stratospheric final warming events. So generally speaking, the stratospheric warming events can be defined as the zonal wind reversal in the extratropical stratosphere. Why we are so interested in these stratospheric events? One example is those stratospheric sudden warmings and final warmings can have substantial influence on the tropospheric circulation. The left panel is the famous results by Baldwin and Duncan 2001. They show the annual mole in the weak vortex events and the strong vortex events. Firstly, the annual mole in the stratosphere basically characterizes the strength of the polar vortex, while in the troposphere, annual mole mostly characterize the meridional shift of the tropospheric jet. What they found here for the weak vortex events, which basically is the sudden warming events, they make the composite for the annual mole for those sudden warming events, and found that this annual mole could extend downward to the surface. This clearly shows that the sudden warming could have substantial influence on the tropospheric circulation. And for the stratospheric final warming, similar results shown here is the high latitude anomalous zonal wind. So basically, it's consistent with the annual mole change. In the final warmings in the stratosphere, which is from 10 hectopascal to around 100 hectopascal, we can see a transition from positive zonal wind anomaly to negative zonal wind anomaly in the stratosphere. This means there is a large zonal wind deceleration in the high latitude, which indicates the breakdown of the polar vortex in the northern hemisphere. If we look at the changes in the troposphere, we see that during the stratospheric polar vortex breakdown, there is also a transition from positive to negative in the high latitude. This means the tropospheric wind, zonal wind, also decelerate, associated with the stratospheric zonal wind deceleration. So all these reanalysis results clearly show that the stratospheric circulation could have substantial influence on the troposphere. The other thing we are interested in the stratospheric warming events is in the southern hemisphere, about the polar vortex breakdown. which is also the stratospheric final warmings. In the southern hemisphere, everyone knows about the ozone hole in the late 20th century. When the ozone hole occurs, there is less solar radiation absorption. This will cause the actual tropical stratosphere to be colder, and this colder will cause the zonal wind in the stratosphere to be stronger, so that the polar vortex will be stronger. And also the transition from wintertime to summertime will be delayed. The left panel here is from Black and McDaniel. They are looking at the breakdown date for the southern hemisphere. So it's stratospheric final warming onset date. They look at the changes from 1978 to 2000. They clearly found a delayed trends for the stratospheric final warming events. And the right panel here, I show is a high latitude zonal wind trend from 1980s to 2001. Associated with that, we can see in the stratosphere there is a positive zonal wind trend, which is shaded right here. And not only in the stratosphere, actually, if you look at the changes in the troposphere, you can see in the summer, those stratospheric signals could extend downward until the surface. So this means that there is also extension for the zonal wind trend. So we are trying to relate this delaying of the stratospheric final warming to the zonal wind trend in the winter time, in the spring of the stratosphere, and in the summer of the troposphere. What we are trying to do is, firstly, consider delayed stratospheric final warming. The dashed line shows the zonal wind transition without ozone depletion. The solid line shows the delayed stratospheric final warming, so we get a delayed transition from westerly to easterly. When this happens, obviously we can get a positive zonal wind trends in the whole transition period. Another way to get a trend is the stratospheric final warming itself changes. Again, dashed line is the stratospheric zonal wind transition without ozone depletion, and the solid line here is the final warming with ozone depletion. So, simply speaking, when the stratospheric final warming is delayed, the transition itself, obviously, the stratospheric final warming will become weaker, and the transition is slower. In this way, we can get a negative zonal wind change prior to the onset of the stratospheric final warming, and a positive change after that. So, based on these ideas, we can make a decomposition for the high latitude zonal wind. Here I show the results for the reanalysis data, the EIA40 data and NCAR data are kind of consistent with each other. The contour line shows the zonal wind, high latitude zonal wind trend, and the shaded area shows the student t-test 95% significance. So we can see this positive trend in the stratosphere and could extend downward to the troposphere. If we make a decomposition for the total trend divided into two parts, the trend of zonal wind due to delayed stratospheric final warmings and the trend due to different pace of the warmings. So basically, when the warming is delayed, it becomes slower. What we found here is this part can explain much of the zonal wind trend in the stratosphere, but the trend due to different pace of the stratospheric warmings can explain much of the signals after the final warming onset and the downward influence on the troposphere.
Excuse me. With the different pace of sudden
Stratospheric final warming.
Is that during one season, or this is in the compilation?
This is more like a for different year when the like without ozone depletion, the transition is more like the dashed line. So there is a quick zonal wind acceleration, so that the final warming will happen. But with ozone depletion, when it was delayed, like at the beginning, it occurs in late November. When it's delayed to say mid-December, this transition will become slower, and the warming will become weaker. So in this way, we will get a negative trend prior to the warming and a positive trend after that. That's what we see here. We have some kind of negative trends due to the different in stratospheric final warmings and the positive trends after the final warmings. Will I answer your question?
Yeah.
Thank you. So these are basically motivations that, firstly, by the prediction of the stratospheric warming can have the potential to better predict the troposphere, and secondly, it could help to understand the dynamic and the chemical processes in the stratosphere and the troposphere. And here about the stratospheric warming events, for example, the sudden warmings, there are two different perspectives about why the sudden warming happens. The first one is tropospheric precursors. Basically, like a recent paper by Matthias et al. 2009, they talk about prior to the sudden warmings, there are tropospheric blockings which are preceding the stratospheric blockings. These are the tropospheric blocking frequency for the stratospheric sudden warmings, for the displacement sudden warming, which is wave number 1 for sudden warming, and splitting, which basically wave number 2 sudden warming. What they found is those blockings happens before the sudden warmings. So there must be some connections between those tropospheric signals and upper stratospheric signals. And more recent paper, for example, by Garfinkel 2010, try to explain this by the interference with the climatological planetary waves. The figure shown here is from their paper, giving the 500 hectopascal wave number 1 and wave number 2 pattern for the geopotential height. The idea is, so this is in the troposphere. The idea is those tropospheric weather systems, for example, the blocking height, if those blocking are in the right location, so that, for example, if the blocking is in this area or in this area, so that they can positively interfere with the climatological planetary waves. In this way, it will enhance the upward wave propagation and causing the stratospheric warming. And if those blockings are in the negative phase right here, so they will interfere with the climatological planetary waves and will damp the upward propagation and cause the stratospheric cooling. So this idea can give more hints about how the tropospheric change causes the stratospheric change. The other perspective, however, is talking about the stratospheric vacillation. Basically, the earliest paper is by Houghton and Miles, 1976. So what they did is using a model by fixing the tropospheric forcing and only leave the stratosphere to change. What they found is when the tropospheric forcing is above some threshold, the stratospheric zonal wind started to have a vacillation, which is transit from westerly to easterly, then go back to westerly. So this stratospheric vacillation doesn't need the tropospheric forcing to change, so that it's internal vacillation in the stratosphere. So those two different perspectives emphasize the different role of the stratosphere and the troposphere in determining the predictability of stratospheric warmings. So we have a question to hopefully to answer is there a way to evaluate the rules of the stratosphere and the troposphere in determining the predictability of stratospheric warming events? So a common way to do this is to do some ensemble forecast. Like, for example, here, the results from Gerber et al. 2009, they did some perturbation experiments to add some perturbation to the troposphere. These perturbations are randomly. So basically, if they add the tropospheric perturbation to the initial condition 60 days prior to the sudden warmings in the troposphere, they couldn't predict the stratospheric sudden warming. Here, the black line shows the 10 hectopascal 60 degree north in the control run, and the greens show the experiments he did. So for those perturbations in the troposphere, if they were added 60 days prior to the onset date, they couldn't predict the sudden warming. But if they added the perturbation 10 days prior to the sudden warming, they could well predict the sudden warming. This kind of experiments can tell us what's the predictability of the stratospheric sudden warmings and its connection to the troposphere. So here, what we did is a little different from what they did. Firstly, the perturbation is kind of different. We use the initial condition we added the perturbation by shifting the initial condition forward and backward in time to see how those initial conditions changes can affect the stratospheric warming events. And secondly is the initial condition perturbations are perturbed separately, not only in the troposphere but also in the stratosphere. And finally, we evaluate their influence on the predictability by looking at the stratospheric sudden warming onset date change. Those onset date is normally defined by the 0 meter per second zonal wind. So we know that the warming itself is defined as the zonal wind reversal. So the 0 meter per second can be regarded as the onset time. I will talk about the perturbation method a little bit later in the slides. But firstly, let me give a description about the model we use. It's a GFD aerodynamic model, a dry model, primitive equation, horizontally are 30 truncation, and vertically are 30 levels. We use Newtonian cooling relaxation, which means we relax the temperature to the prescribed zonal symmetric equilibrium temperature. In this way, the equilibrium temperature can drive the temperature and the circulation. The left panel here I show is the zonally symmetric equilibrium temperature we use in the stratosphere. In the northern hemisphere is a stratospheric winter, and the southern hemisphere is a stratospheric summer. The right panel is the radiative zonal wind calculated from the equilibrium temperature field. So basically, from the thermal wind relation, we can see there is a polar vortex in the winter hemisphere and a easterly jet in the southern hemisphere. What we use this equilibrium temperature is, firstly, we can fix this equilibrium temperature and run it for thousands of days to get the perpetual winter results. If given the proper topographic forcing in the perpetual winter, which is in the northern hemisphere, we can get numbers of sudden warming events. And since the final warming is the spring transition from winter polar vortex to summer easterlights, we also need the seasonal transition of the equilibrium temperature to drive the model to get the seasonal transition of the circulation. The bottom equation I use is the equation for the equilibrium temperature. It will give a seasonal transition from winter time to summertime. At this time, we can get a spring transition and the stratospheric final warming events.
Yeah, I just have a question about your radiative equilibrium zonal wind. So why do you choose your temperature only specify the vertical shear? So how do you choose the 0? Or because it's strange that it's sort of a little bit unusual to have an easterly radiative equilibrium jet.
You mean
in the troposphere?
Oh,
yeah, because your wind shear actually, if you start with 0, then it's westerly.
Right.
Even in the southern hemisphere. So.
Yeah, I'm sorry that this could be kind of misleading because the equilibrium temperature basically the winter summer only in the stratosphere.
Yeah.
In the troposphere, we use the standard Held and 3-rise 1994 sighting. So it's hemisphere symmetric, and this is I should cut from here. This just we are trying to say consistent with the paper by Scott and Haney is used because we use the same equilibrium temperature as they use. They use here in their paper they use it only in the stratosphere, but here this doesn't mean anything. So next, I want to mention about the different topographic forcing influence on the stratospheric circulation. These 3 figures are all for the perpetual winter zonal wind climatology, but with different topographic amplitude. This equation gives the topography we use. It's an idealized topography. M equal 1, so it's with number 1 topographic forcing. This H0 basically determines the amplitude of the topographic forcing. When the amplitude is lower, we can get a stronger polar vortex in the stratosphere, and the jet of the stratospheric vortex is around 60 degrees north. But when this topographic amplitude increases to 2,000 meters, we can see the vortex becomes weaker, much weaker, and shifts forward. So this is because more planetary waves will propagate into the stratosphere as the amplitude increases. And those planetary waves will tend to weaken the polar vortex and shift the jet forward. And this 1,000 meter case is more like the southern hemisphere winter, and this 2,000 meter topography forcing, the result is more like northern hemisphere, like I showed at the beginning of the slides. The northern hemisphere polar vortex is much weaker than the southern hemisphere. So in the simulations, we use different topographic forcing to simulate northern hemisphere-like and southern hemisphere-like polar vortex. And for the seasonal transition with 1,000 meter topography is more like the southern hemisphere final warming. For the 2,000 meter topography, seasonal transition will be more like a northern hemisphere stratospheric final warming. This is just to some observational final warmings from the reanalysis. These results are making the composite for the final warmings, shows the high latitude zonal wind transitions. Day 0 is the onset date of the warmings. So from the across the stratospheric final warmings, we can see there is a transition from westerly to easterly, showing the breakdown of the polar vortex in the stratosphere. And the northern hemisphere, the transition is much more abrupt than the southern hemisphere. The zonal wind transition in the southern hemisphere is much slower than the northern hemisphere. And in our model, we can also do that. Here, what we show in the top panel is the 50 hectopascal, 70 degree north zonal wind evolution. And here, for 2,000 meter final warming and 1,000 meter final warming. As I said, when the topographic forcing increases, the polar vortex will weaken in the perpetual winter, and the transition from westerly to easterly will be much more abrupt than in the 1,000 meter case. And this large zonal wind acceleration is consistent with the Ellison-Palm EP divergence in the high latitude. Here I show the 50 hectopascal EP divergence in the high latitude. We can see larger EP convergence, which is much larger value compared to the low topographic forcing, so that this transition will be more abrupt than in the 1,000 meter case.
I just have a question about the experiment set up there. Because here you are basically forcing the deceleration is completely due to planetary waves.
Oh yeah.
But in the real atmosphere, you would expect that part of the deceleration is due to gravity waves, and so your planetary waves, would that suggest that your planetary waves are too strong to start with, and so the difference between these because maybe enhanced because of your experimental setting?
Here I'm trying to show that when the planetary wave becomes stronger, the transition will become quicker, like the northern hemisphere and the southern hemisphere. similar to the observations in the final warming transition in northern hemisphere and the southern hemisphere.
Yeah.
Does that answer your question?
Yeah, we can talk about that.
Okay. And here I also show some simulation results for the stratospheric southern warming. It's for the 10 hectopascal high latitude zonal wind evolution. Again, we see 0 meter per second is here. There is a transition from westerly to easterly. And this large zonal wind deceleration in the high latitude is associated with EP convergence when it goes to the southern warming onset. So this means that those waves from the troposphere are working, trying to decelerate the stratospheric zonal wind. The bottom two panel is the 10 hectopascal geopotential height. The left panel is the mid-winter state, and the right panel is the onset of the southern warmings. We can look at that. So in the typical winter, the geopotential height shows a low, so which is the polar vortex we normally see. But when the southern warming happens, we can see this polar vortex is displacement of the pole, and there is a high pressure center. This means a large amplitude of wave number 1. This comes from the topographic forcing, because we use wave number 1 topographic forcing, so we get a displacement southern warming. But if we use wave number 2 topographic forcing, we will get a kind of wave number 2 pattern, so it's more like splitting southern warming events. So a little bit more about the perturbation method we use. We do two types of experiments. One is at day minus 10, one is at day minus 20. What we do the experiments is we shift those initial conditions forward or backward a little bit. And the same thing for the day minus 10 initial conditions, we shift the initial condition forward or backward. This is the equation for the perturbations we use. So for the total perturbations, we basically use the perturbation, we use the control run TP, which is kind of like from day minus 29, minus 27 to day minus 11 to replace the day minus 20 initial condition. In this way, we can observe that how the stratospheric final warming of southern warming onset date changes associated with the initial condition perturbation changes. And we can also do that for the stratospheric perturbations, tropospheric perturbations, by shifting the initial condition only in the stratosphere or only in the troposphere. So this just a short summary about we have 12 southern warmings, 12 final warmings with 2,000 meter topography, and 12 final warmings with 1,000 meter topography. And for each warming event, we do the forecast experiments with the minus 20 and the minus 10, and with total stratospheric and tropospheric perturbation separately. Those are the results for the total perturbation. The line with the asterisk is for the total, it's for the control run zonal wind evolution. I only show 50 hectopascal, 70 degree north zonal wind. So this is the control run. If we shift the initial condition backward, we will get something like this. If we shift the initial condition forward, we will get the transition quickly, so that the 0 meter per second will be the onset date. So if we shift 10 days, shift backward for 10 days, we will get a final warming onset date around 10 days. late. And if we shift the initial condition forward for, like say, 5 days, we will get the onset date 5 days earlier. So this means the initial condition can basically determine the predictability of the final warming events. And this schematic graph just to show how the shift in time for the initial condition determines the shift in time for the warming onset date. So basically, if there is no shift in time for the initial condition, it will be the same as the control run and everything is 0. But if we shift the initial condition backward, say the control run initial condition is at day minus 10, then we get the warming onset 10 days after that. So if we shift the initial condition back to day minus 12, we will expect to get the warming onset 12 days after that. So we will get a late final warming onset. So this will give an basically exact -1 slope for the linear relationship between the shift in time for the initial condition and the shift in time for the warming onset date. And sometimes, like if we only shift the tropospheric condition, initial condition, or stratospheric initial condition, it only changes part of the stratospheric warming events, then the slope will kind of like this, between 0 and -1. At this time, the changes of the initial condition in the stratosphere and in the troposphere, the shift in time can only partly contribute to the shift in the stratospheric final warming or sudden warming events. So how does this work? We can simply integrate the zonal wind from the initial condition at day -20, day -10 to the warming onset, which is 0 meters per second. And this way, we can get a basically 0 minus the initial condition to be the integration of the zonal wind deceleration. This is so that this will be determined by the average zonal wind deceleration rate times the difference in time. From this equation, we can get the changes of the onset date can be approximately expressed as the a function of changes in zonal wind initial conditions and changes in zonal wind deceleration rate. So basically, there are two ways that stratosphere or troposphere can determine the predictability. The first one is the stratosphere can provide the initial state of zonal wind for the final warming. So if this UTI, the initial condition, is becomes larger, we will tend to have a late final warming or sudden warming because it will take a longer time to decelerate the wind to 0. And on the other hand, if they can affect the eddy forcing prior to the final warmings, they could affect the Edison pump EP divergence, and this will connect it to the zonal wind deceleration. So in this way, they can affect the DUDT evolution, so that also partly determine the predictability. So in order to look at this, we can look at the left panel shows the tropospheric experiments, and the right panel shows the left panel shows the stratospheric perturbation experiments. The right panel shows the tropospheric perturbation experiments. For the stratospheric perturbation experiments, we can see at the beginning there is large diverge, because if we shift the stratosphere backward, we will get a larger zonal wind. Forward, we will get a less zonal wind. But the interesting thing is it's kind of different from the total perturbation is that they tend to follow the same zonal wind deceleration rate so that this diverge can gradually become smaller so that stratosphere only determine part of the predictability. If we look at the 0 meter per second to get the onset date. And for the tropospheric initial condition, tropospheric experiments, at the beginning, it can start from the same points because we only perturb the troposphere. The stratosphere is doesn't change at the beginning, but they tend to follow the different zonal wind deceleration rate so that the evolution tends to diverge as time goes, so that it will partly determine the predictability by affecting the zonal wind deceleration rate in the stratosphere. Similar thing for the D-20 initial condition experiments. So here I show the Elysium time divergence results just to compare the total perturbation experiments, the stratospheric perturbation experiments, and the tropospheric perturbation experiments. So for the total perturbation experiments, we see the control round and the perturbation round, which is the perturbation round just shift forward or backward, follow the initial condition. But the stratospheric perturbations, it's tended to the first order, it's more similar, follow the control round for the EP divergence evolution, while the tropospheric perturbation rounds, it's more similar to the total perturbations. So this means that to the first order, the stratosphere affects the predictability by providing the initial condition for the stratospheric warming events, while the troposphere have a large impact on the eddy forcing so that it determines the zonal wind decelerations in the high latitudes. So roughly speaking, the stratospheric and the tropospheric perturbation experiments resemble the initial condition without changing the eddy forcing evolutions, and eddy forcing evolution perturbation experiments without changing the initial conditions. So in order to test this idea, we want to do some experiments only perturb the initial conditions without changing the eddy forcing evolutions, or we want to do some experiments only changing the eddy forcing evolutions by shifting the eddy forcing evolutions forward or backward, but without any change to the initial state. This cannot be done in the full model because the zonal wind and the eddies are basically coupled with each other. But in the zonal symmetric model, we could do that. This zonal symmetric model is similar to the full model I just showed, but only zonal mean field. So wave number 0 are integrated every time step. And the eddy forcing evolution in the full model can be diagnosed. And the zonal symmetric model with the external eddy forcing from the full model, we can reproduce the full model results approximately. And what we've done here is try to compare the full model with the zonal symmetric model, and we, as I said, in the full model we did some stratospheric initial condition perturbation experiments, and we did some tropospheric initial condition perturbation experiments. And we can do it this way in the zonal symmetric model. We can do the initial condition perturbation experiments, or in the zonal symmetric model, since we can diagnose the external eddy forcing evolutions, we can use the same eddy forcing evolution, the same as the control round, so that only initial state changes. And we can also shift the evolution of the eddy forcings in time with the same initial condition as the control rod. So in this time, we can compare this initial state perturbation results with the full model and compare this shifting the evolution of the eddy forcing in time with the tropospheric initial condition perturbations. We test the difference. We test the delta T0, which is the onset date change divided by the initial condition change in time. So this is basically the slope what I show here. So these are the results for the 2,000 meter stratospheric final warmings. This shows the D-10 initial condition experiments and the D-20 initial condition experiments. What we found is, to large extent, the stratospheric perturbation experiments give the consistent results to the zonosymmetric model initial condition experiments. And the tropospheric perturbation experiments show similar results to the zonosymmetric model eddy forcing evolution perturbation experiments. So this kind of confirm our hypothesis that the stratosphere affects the predictability by providing the initial condition, and a troposphere have a large impact on the eddy forcing so that it determines the predictability. We can also do this for the sudden warmings differently. This is for the D-10 initial condition. We can see both the stratosphere and the troposphere could contribute to the predictability of sudden warmings. For D-20 perturbations, interestingly, we see the perturbations with different initial conditions, but they don't change the onset date that much. Instead, we can see with the tropospheric perturbations, it changes the onset date a lot, so that most of the predictability is determined by the tropospheric perturbations. And we can also do the similar comparison for the sudden warming. For the D-20 initial condition, consistent with the previous slide, we get the troposphere determines basically all of the predictability. For the D-10 initial condition, however, we get a troposphere also determines part of the predictability, but there is some kind of inconsistency between the full model stratospheric perturbation experiments and the initial state perturbation experiments in the zonosymmetric model. This inconsistency is basically come from the stratospheric eddy feedback. Basically, when the stratosphere, when it's very close to the onset date, the changes in the initial state will changes the eddy forcing in the stratosphere, so that the sudden warming onset will changes a lot. So finally, a short conclusion is, to the first order, the stratosphere affects predictability primarily by providing the initial condition, while troposphere have a large impact on the through the generation and propagation of planetary waves. And secondly, the stratospheric eddy feedback is generally not important except for initial conditions very close to the onset date. Finally, our result highlights the tropospheric rule in affecting the stratospheric eddy feedback, eddy forcing, and providing predictability for the sudden warmings. That's all. I want to take an end and take any questions. Thank you.
where you held the troposphere kind of with the almost climatological.
Yeah. Yeah.
And the other half you let it run. Your conclusion was there was more perturbation coming again from the troposphere.
Yeah.
That logic I didn't quite follow. If you held it that way, what is going on? Because if it's on the climatological run,
Yeah.
how would it affect, say, the editing? Maybe I'm missing something.
I'm sorry. Which slide are you talking about? Okay. So you're wondering like the connection of the troposphere to the stratosphere.
Actually, I was wondering the logic why you held the troposphere on climatological mean, why you are playing with the troposphere, but then you come to conclude that the disturbance is coming from the troposphere.
Actually, so I think, well, they did both types of studies. In one set of runs, they held the stratosphere constant and perturbed the troposphere. And in another set of runs, they did the opposite. They kept the troposphere as fixed and perturbed only the stratosphere, just to see if which has the greater impact.
This figure?
Keep going. It's a couple down.
So that is what they
That one.
did.
This one? Like if we look at this figure, it shows how the changes in initial condition in the tropospheric in the stratospheric initial condition affect the changes in the onset date. So basically, if we shift the stratosphere forward or backward, it doesn't have changes in the onset date. Means this kind of stratospheric change is not important in determining the predictability. Instead, here we can see even when we make a perturbation to the initial condition in the troposphere, the onset date in the stratospheric warming will transit associated with this change. So there is a very good around like -1 slope. So this means the onset date of the southern warmings is connected to the changes of the tropospheric initial conditions. So in other words, if we shifting the tropospheric initial condition forward or backward, we can get the warming in the stratosphere to shift backward or forward. But we cannot do that. We cannot get that by changing the stratospheric initial condition. So this means troposphere is very important, basically determining all of the predictability in this experiment. Does this answer your question?
Yes. Peng Liu has a question.
Yeah, a question about the onset. First, about the date. If we look at the ERA40 data from 1980 to 2001, we'll have over 20 years. For each season of those 20 years,
Yeah.
if we analyze the onset date of the warming, will those dates be pretty much be close to each other, or you have hard year-to-year onset dates?
So you're talking about this slide, right?
When does the stratospheric final warming event occur?
Normally it's in late November to, you can see late November to around December.
That's the southern hemisphere, right?
That's southern hemisphere.
Yeah.
But the point is it changes every year. It is
What
different.
is the trend here? What is the trend? Is it getting later?
Yeah, it's being delayed.
Being delayed.
Yeah, it's being delayed. We can see there is a trend toward this. So this is kind of November. This is kind of January. So the final warming is delayed.
In the southern hemisphere.
Yeah, in the southern hemisphere.
Because of ozone depletion.
Is there any trend in the northern hemisphere?
It's not that it's not that significant in the northern hemisphere. Basically, because the polar vortex is much weaker, and this transition, the northern hemisphere has a larger internal variability, interannual variability, rather than the trend.
So the spread there from year to year would be larger in the northern hemisphere.
Exactly.
Big changes.
Exactly. We calculated like the standard deviation.
February and April or whatever.
Oh yeah. It's kind of like from March to May.
Yeah.
Thank you.
Second one of locations. Even in the northern hemisphere, we know that topography is not equal only.
Yeah.
We will have Eurasia, we will have Australia.
Yeah.
Is there any location difference of the warming? You're using the normal mean, of course.
Yeah.
Not as difference in the zone direction, which will be the preferred location for the first onset warming.
Yeah. Personally, I haven't looked at specific location where the warming first to occur, but I don't think it's so close to the those topographic places. In the stratosphere, if we look at the circulation, it's a little bit zonally symmetric. That's the main difference from the tropospheric circulation. So yeah, I don't think that
So actually, the answer to that is that in the winter there is a vortex, right? But sometimes in spring, initially the vortex get displaced from the pole, and another springtime events it gets split into two. So it's difficult to tell where it is taking place, but there is a change in the circulation that is very noticeable. I want to see if there is. Shoichi, do you have a question?
Yeah. I'm a little bit confused by your perturbation method.
Okay.
You said you shift the initial condition backward or forward.
Yeah.
And does it mean that you run the initial condition of the -10 days to run it from the -12 days, for example?
Yeah.
To do it? What's the difference between you run the initial condition from -12 days and just run the initial condition here for 12 days?
You mean what's the difference?
Yeah, I saw that you say you, for example, shift the initial condition from the -10 days to -12 days.
Yeah.
So that means you run this initial condition from the -12 days.
Yeah.
But is this difference between that you run the initial condition from -12 days to the +2?
Yeah.
What's the difference?
The difference, I think, is kind of the radiation is a little different. Like for the signal transition, if you use the D-10, if you start with the D-12 initial condition, the equilibrium temperature will be a little bit different. But this basically doesn't affect the results that much, which can be seen from the total perturbation experiments. So the transition basically just shift forward or backward without substantial change.
Yeah, I have a question there. So when you shift the stratosphere and troposphere separately, presumably there's some balance.
Yeah.
Vertical. So how do you maintain that? So if you shift by 10 days, say that's a big shift between the stratosphere and troposphere.
There is some kind of adjustment when we do that, separately in the stratosphere and the troposphere, and we look at that. Looks like it doesn't affect the circulation that much. So basically, when we look at the onset date, the adjustment already done. So it doesn't have much influence from what we see in the results. Yeah, we kind of look at the zonal wind transition for the perturbation rounds and compare with the climatology, if we only perturb the stratosphere or if we only perturb the troposphere. We didn't see clear effect of this greenhouse.
And what you see as eddy field being transmitted couldn't be internal, more of internal waves because you split it like that?
Yeah, very good question. From our results, it looks like it can follow the tropospheric initial condition. It's small, like especially for the sudden warming, the day -20 initial condition. If we shift the tropospheric initial condition, those eddy forcings following the initial condition, those eddy forcing evolutions tend to shift following those initial conditions in the troposphere. And it doesn't change that much.
So there are no more questions, so let us thank our speaker, Professor.